let's take a crack at that flea problem. What we have is a flea standing on the ground. I'll call it in a crouched position. It jumps up and leaves the ground with a velocity that I'll call v2, and then flies into the air up to a height I'll call y3, where it's got v3 is equal to 0. Here it's got v1 is equal to 0. So we've got two distinct phases of the motion. So from here to here, the flea is in the jumping action. That is, it's pushing down against the floor and raising its center of mass. It raises it just a tiny amount that I'm going to estimate, based on fleas that I've seen in my life, that the amount it raises it is delta y. I'm going to call it delta y, is just a millimeter. So it raises itself about a millimeter, and at that instant, after it gets a millimeter up, its feet are just barely losing contact with the floor, and from then on it's just in free fall. So we've got two distinct phases: the jumping phase and then the free fall phase, where it's just moving through the air. I'm going to neglect air resistance. That might not be a great approximation, but I'm going to neglect air resistance. And because, like, for one phase, this is the before picture and that's the after picture, and for another phase, that's the before picture and that's the after picture, instead of having to have two sets of before and after pictures, 4 diagrams altogether, I'm just going to use these, and I'll call them 1, 2, and 3. And this will be my reference level. So let's talk about the idea. This part of the problem is kind of easy to figure out how fast it had to be going in order to get up that high. That's just there's no energy coming into the system. It has already come into the system in phase 1 to 2. But in this phase, I can just use conservation of energy to say, based on the potential energy it has in the after picture, how much kinetic energy it has in the before picture. Then this phase is really what the question is all about. If I know how fast it's going after it's gotten its center of mass up a millimeter, I can use the idea that I'm going to approximate the acceleration as being constant. There's no guarantee it's constant, but I'll treat the acceleration as constant. I'll use the constant acceleration equation to find out what the acceleration would have to be to make it go from a velocity of 0 up to a velocity v2, whatever we find that out to be, based on the fact that it can jump 30 centimeters off the floor. That's my method for solving the problem. Conservation of energy from picture 2 to picture 3 to get v2, constant acceleration equation from picture 1 to picture 2 in order to find out what the acceleration is. So during this phase of the motion, from 1 to 2, it's got an acceleration that I'm going to call a. From here to here, it's got an acceleration that is g in the downward direction. This one is going to be upward. So I want to find out what a is. Alright, let's go for it. Let's do what I just said I was going to do. Conservation of energy for 2 to 3. So I'll start off with E2 is equal to E3. Then it's always the same from there. K plus U. So we got K2 plus U2 is equal to K3 plus U3. Alright, in this picture, I'm going to treat, it's at a height Y2 in this picture. when you're making approximations, what matters is what you're comparing things to. So compared to 30 centimeters, how high it's going to be in this third picture. Y2 is negligible. So I'm going to say the potential energy in this picture is 0. The insect is roughly at the reference level. And then by the time it gets to its highest point in the jump, of course, its velocity's got to be 0 when it's up there. And therefore it has no kinetic energy. The energy of motion is 0. Alright, so this is 1/2 the mass of the flea times v2 squared is equal to mg times y3, how high up it is in this third picture. And I'm trying to get v2 out of the deal. v2 is equal to square root of 2gy3. If you plug those in, I think you find it's like 2.5 meters per second. So pretty small compared to people who looked it up on the internet at ask.com. They said they found it to be like 11 point some odd meters per second. But if it was moving that fast, then it would go up a lot higher than 30 centimeters here. That 30 centimeters is kind of hard to read. So let me try writing that a little bit more neatly. Okay, more legibly. So we got how fast it's going in this picture right here, and that was using phase 2 to 3. Phase 2, 3. So in other words, from instant 2 up to instant 3. Now let's use 1 to 2 to get the acceleration. Alright, we don't have the time. We're not looking for the time. The time would be hard to estimate. I wouldn't want to try to guess how long the feet are in contact with the ground. That would be something interesting to solve for. But I was willing to estimate that, how high it lifts itself during the pushing off the floor phase is about the size of a flea, which I estimate to be on the order of a millimeter, the height of a flea. So we're using the one that doesn't have time in it, and that's the v squared is equal to v0 squared plus 2a delta x. And I can write that down immediately off the formula sheet in terms of the symbols that I've got in this problem, and that is v2 squared is equal to v1 squared plus 2 times the acceleration. I called it just plain a times delta y. I'll let my coordinate system, I'm going to call that the positive y direction, so that's the y-axis, with this being my y is equal to 0 right at the reference level. v1 is 0. Before the flea started its jumping action, it wasn't moving, and we're looking for a, so let's go ahead and solve that for a. I get a is equal to v2 squared over 2 delta y. I'll go ahead and plug in what v2 is from what we found. So I'm going to tell the reader where that came from just in case they can't see it. So right there. That's my plug-in to get this result, and it's got to be squared and then divided by 2 delta y. Alright, I think we're in good shape here. So A is equal to just 2gy3. Square the square root is just whatever was inside in the first place, delta y. The 2's cancel. I'm going to write that as y3 over delta y times g. Now if I wanted it in SI units, I would plug in values for everything, including the 9.8 meters per second squared for g. But he wants to know how many times g it is, so instead of doing that, I'll just leave the g in the answer. So y3 was 30 centimeters, that's 0.3 meters, and delta y was 1 millimeter, 0.001 meters times g. And so A is equal to 300g is the estimate for the acceleration. And the approximation came in right here when I estimated how far up a flea's center of mass moves during that jumping phase while it's all actually pushing off the floor. So that does it for the flea problem.